Okay, so the most useful base for exponential logarithmic functions is the number denoted by the letter e. It's just like pi, it's an irrational number. Okay? And E was named after a famous mathematician, Euler, spelled E, I should capitalize it, but E-U-L-O-R. Euler. Some of you wrote, there's a math contest called Euler. I always call it Euler, but it's actually Euler when you actually look it up. Huh? It is E-R. I spelled that wrong, didn't I? I'll try again. E-U-L-E-R. There you go. That's how you spell it. I'm like, it didn't look right. Anyways, so if I keep on plugging in numbers here for n, that you will end up getting, this is actually your first kind of showing of calculus here. If I keep on plugging higher and higher and higher and higher numbers, at some point there's going to be a limit to how high it's going to go. And that's the first topic that we actually talk about in calculus. So as I showed you in the graph, the height was about 2.718. There is a 2.718 on your calculator. Can you find it? It's on the graphing calculator, it's the second function of ln, right below your log button. So, but you have to do that to the power 1 if you want to see the number 2.718281.
Division?
Yes, second function division is also e. So if you just do that, that'll just be e to the power 1. Okay, so again, try to punch this into your calculator in your y1. So go bracket 1 plus 1 divided by n to the power n. And see if you can get the table set values. So again, go to your table set, start at 1. And then what do you get for your number? You get 2. Go to your table set. Start at 10. Look at your table. What do you get? 2.5937. Does everybody know where they're going? Go to their table set. Start at 100 this time. Go to table. What do you get? 2.7048. Go to your table set. Go to 10,000. And then to your table, you get 2.7181. Okay, so again, E is not a variable. It is a constant number, I guess. That's what I'm looking for. Because it's not irrational. And irrational, it would be a... Okay. Used for exponential growth. Okay, so it's used for exponential growth and exponential decay. In word problems, it would be determining compound population problems, compound interest problems, or half-life. Have you heard of half-life before? Okay, so we're going to graph this, and just so that you can realize what this looks like, we're going to graph 3 to the power x. So how do you graph 3 to the power x? Yeah, it's at 0, 1, and then at 1 it's at 3, and then at -1 it's at, a third, right? And it looks like this, yes? And then we have an asymptote here. So that's y equals 3 to the power x. So where do you think e to the power x would be? What's e as a base? 2.71 roughly, right? So still going to go through 0, 1 because why? E to the power 0 would be 1. At 1, it wouldn't be at 3, it would be at 2.7, right? Now, what would be, is this going to be below 1/3 or above 1/3? Yeah, so E is smaller, right, than 3. So if you reciprocate it, it'll be bigger, so it'll be above. So it's essentially a 3 to the power x graph. Like, it's not really that much different. Yes? That's what I'm saying. Today is almost like a review because all I'm doing is showing you with a different base. So the asymptote is still at y equals 0. The y-intercept is still at 1. The x-intercept, there is still none. So then, of course, we have transformations with the e to the power x. So how would we do these? Well, first we would draw the e to the power x graph. So again, I would use the 3 to the power x graph and just do slightly under, right? So 1, 2, 3, 1, 1, y, x, here's a 3, here's a 1, just to give my scale. It's going through 0, 1. At 1, it's going through there, and it's there. So here is my e to the power x graph, yes? So who can tell me what actually happened here with those 2 negatives? Who can describe what happened for transformations? Reflection, how? Yeah, it's 2 reflections over x and y axis. Does anybody remember when a function is itself, when it's reflected in 2 things, what that's called? Not even. Odd, yes, it's an odd function. Okay, so we're going to reflect it here and then reflect it over the y. So do you see that that 0, 1 would still be on the axis? Does that make sense to you? Okay, so at 1e, it gets reflected here. Maybe I'll have to go here. So over and then down there, yes? And then this, again, you could say it's approximately 1/3, but anyways, it gets reflected there and then reflected over, right? So it looks like this. So this is g of x. Yep. So what's my asymptote? Still y equals 0, yeah? And what's my y-intercept? -1. Perfect. Alrighty. Ooh, what about this one? Okay, so let's graph our base graph. Oh. 1, 2, 3, 1, 2, 3. So at 1, 0, 1, at 1, it's just a little bit below 3. I don't know why there's a dot over there. I'll get rid of that. Okay, so here is my y equals e to the power x. So what's going to happen first here? Are we going to make it an asymptote or shift it? Is it shifting right or down? It's going down. If I wanted it to go right, it would be part of the exponent, right? Okay, so we're going to go down. I suggest drawing this twice because this is a hard one to do on your own. So I'm going to shift it down first. So that's, does everybody see it's down 1, then it's a half reflection to positive y values. Well, because anything that's below is the only thing getting affected, right? The rest stay the same. Yeah? Okay, so I'm going to go down 1. So this goes to here. This goes to here. And that goes to, say, there. Yeah? And where's my new asymptote? Right there? Oh. Yes? So this is y equals e to the power x shifted down 1. Everybody agree? Okay, so now I'm going to use red. And what's going to happen with this absolute value? Does everybody, yeah, so does everybody see this is going to stay the same, right? That's why I'm calling it a half reflection, because all the positive y values are staying the same. And after this, what happens to this asymptote? It's going to get reflected, so where's my new one? It's at +1. And how is this going to work? It's going to hit the 0, and then it's going to go like Isn't that kind of a cool looking graph? So again, on my green, the positive stayed the same, and then all I'm doing is reflecting this over the y-axis, right? So this green became this part, right? So then my asymptote is y equals 1 now. And what's my y-intercept? 0. Okay, how do we think about the e to the power x graphs? Pretty easy. Okay, so now I'm going to introduce what's called the natural log. So if you have a log that has a base of e, it's called the natural log. The inverse of the exponential function y equals e to the power is y equals ln x. So here's the thing that you need to know. All that's different here is instead of we could write it this way, but it's so common that they came up with a shortcut way of writing it, and that's the natural log ln. You hear some people call it ln. I never understood why they called it ln of x, but that's how people say the natural log. I'll always say the natural log. I don't know, it's just I don't know, they say ln x. So anyways, all you have to know is just a log that has a base e. Like the common log on your calculator, log, it's just a base 10. This is a base e. It's not like it's a different log, it's the same kind of log, it just has a different base, right? So the natural log function is usually written as ln. Ln, or ln, is the abbreviation for natural log. I don't know why I wrote it so many times, but yeah, get it? Okay, so how do we do this? The natural log graph. Well, let's graph. We already know how to graph e to the power x, so let's start with e to the power x then. 1, 2, 3, 1, 2, 3, because we're good at e to the power x. Remember, it goes through 0, 1. At 1, it's at 2.71, and at -1, it's, say, approximately a third. But not really, right? So this is my y equals e to the power x. Remember, this is an inverse function. So what does that mean? Yes, it's a reflection over the y equals x. I switched the x and the y around. So what does 0, 1 become? 1, 0. What does 1 e become? E, 1. E is 2.71. So just before 3 at the height of 1, that's where it's going to be. Do you see that? And again, this is 1 over e. Sorry, -1, 1 over e. So it'll become 1 over e, -1. So that's essentially, again, if you just approximate about a third, it's like, say there. So looks like a log graph, doesn't it? Yeah? So again, when you draw this, your 3 points, I would just use the base 3 graph. Nobody's going to like measure up, oh, it's not really 2.7, it's really 2.8. No, they don't care. They want to know if you can get the shape, right? So that's why I said use base 3 graph. It's just a little bit short of 3, of course, 2.71. It has to go through 1, 0, because all of them have to go through that, right? And then I would just use a third as an approximate there, right? And we're just going to be transforming these 3 lines. So what's the asymptote here? X equals 0. What's my x-intercept? 1. Okay, what do you think is going to happen for this one here? It's a reflection. So the x's become negative x's. So what is that? Reflection over the y-axis? Yes? Okay, so do you want to draw the base graph? Okay, so let's do that. So 1, 2, 3, 1, 2, 3, right? It has to go through, again, 1, 0. At 2.71, it's a height of 1. At -1, it's, say, there. Oh, I'm a little bit off. I'll try that again. Okay, so now we're going to reflect it over the y-axis. So I'm going to use red. I'm going to use red. So this becomes there. Everybody agree? And then 1, 2, 3, approximately at negative e, it'll be at 1. And then, really, that's what we're looking for. Right? And the asymptote's in the same spot, right? Any questions there? So what's my asymptote? X equals 0. What is my x-intercept? Negative 1. Okay, now we have 3 things going on here. So who can describe what happened in C here? Yep.
It's a reflection over the x-axis.
Okay.
It goes up 1 and right 2, left 2.
Yep. Left 2, up 1, or up 1, left 2. Very good. Okay, so I'm going to start with my base graph again. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Okay, so remember, in order not to get error codes, you got to label your x and y axis, and you got to establish a scale, right? So 0, 1, 2.7, 1, like that. I don't like how I started that. I think it's easier to start the other way. Go this way. Oh, I erased too much now. The reflection over the x-axis. So do you want to do this all at once, or do you want to do it in 2 steps? Do we want to do the reflection, draw it, then go left 2, up 1, or you want to do it all at once? Ah, I like that. Okay, let's do it all at once. Okay, so we're going to reflect over the x-axis. So 1, 0, if it's reflected over the x-axis, what happens? Stays the same. Then we're going to go left 2, 1, 2, up 1. Did everybody see that's my new 1, 0 point? Okay, how about this one? E1. It gets reflected over the x-axis. Now it's at E negative 1. Then we're going to go left 2. This is a little hard. 1, 2. Yeah, and then up 1. Like that, say. And then this one is even harder. So this is now going to get reflected, right? Yes. So up to there, then left. This is at 1/3, right? So 1/3, 1/3, so there, and then up 1 there. So where's my new asymptote? That's probably the easiest way to figure this out here, because my dots don't mean anything at this point. It looks kind of goofy. Okay, so if I reflect my asymptote, nothing happens, right? It just, well, I guess it, in a way it does. It's over here, right? Okay, then I'm going up 1, which doesn't affect it, and then left 2, so it'd be at negative 2. So you might want to have it kind of going like this. So now, can you see the graph a little bit better? Yeah, that totally helps it. So, of course my pen is like goofy. Let's try this again. So I'm going to go with my asymptote, and there we go. Looks like that. Yeah? Okay, what's my asymptote? X equals negative 2. What's my x-intercept? Oh, I don't know for sure. So how do I figure this out? Is that E? No, E is 2.71. It can't be.
minus 2. Yeah.
Okay, so how do we do this algebraically? You learned this in grade 10. If you want to find the x-intercept, you put y in for 0, solve. If you want to find the y-intercept, you put x for 0 and solve. So if we want to find the x-intercept, we're putting y to 0. So 0 equals negative ln of x plus 2 plus 1. So now what do I do? Move the 1 over, right? Negative 1 equals negative ln x plus 2. What do I do now? You could say divide by negative, but just switch the signs, right? So 1 equals ln of x plus 2. Now, how do I solve a log graph? We learned this yesterday or 2 days ago. Exponentialize, right? So, what's the base of this? E. So, e to the power 1 equals x plus 2. So, x-intercept is e minus 2. And that's exactly what you said. So, good job. All right. Okay, log theorems. We can use all of the log theorems with natural log. So you remember how to expand this with the common log, or a base log of 2 or whatever? The numerator becomes addition, and the denominator becomes subtraction. The exponents become coefficients. So I'll give you a second to do this one. I'll give you very good. Okay, 2 ln x plus 3 ln y minus 1/2 ln z. I'll put a little slash through my z so it looks like a z and not a 2. Okay, now we're going to write this as a single log. So this is going to become ln of what? I'll give you a second if you can find the what. B? Okay, so I'm going to put a line here. The numerator would be x minus 1. Oh, and then this one would be x plus 3 to the power 3. And then this would be what? The square root of x squared plus 2. You could also have x squared plus 2 to the power half. Yes? Did everybody get that? Okay. Here's some little shortcuts I think you should memorize. What do you think of log e base e is equal to? Yeah, it would be 1. It's just like when you have log of 3 base 3 or whatever, right? If they're matching, it's 1, because that's the only way it could be the same. So that means that ln e is 1, because this part essentially means that, right? So anytime you see ln e, that's equal to 1. So here's the thing. So yesterday I showed you how to solve exponentials, and you logged both sides to solve. So if you ever see an e in the question, it is way more easier to natural log it because of the fact that ln e equals 1, and then you'll make things 1 everywhere, and that's simple, right? So 2 exponents, I can't change it into log form, but I can log both sides. In this case, I'm going to natural log both sides. Does everybody see what I did? So now, if we use the log theorems, that means the x goes in front, and this goes in front. Is everybody good with that? So then I get x ln e equals bracket x minus 1 ln 2. Everybody good so far? We just finished saying, what is this equal to? 1. It goes away. And some people, after you do this a couple times, as soon as they ln this side, they'll just go directly to x, because they know that's what happens, right? Okay, and then of course on this side you get x ln 2 minus ln 2. I multiplied this out, right? What's the next step? X is on one side. X minus x ln 2 equals L. Oh, you know what? I'm going to move it the other way because then I have more positives. So ln 2 equals x ln 2 minus x. You don't have to. It's just easier to punch in your calculator, right? So I'm going to factor out the x. So x bracket ln 2 minus 1 equals ln 2. So x equals ln 2 divided by ln 2 minus 1. Did I do that too fast? Okay, let's punch this in. Did everybody find their ln key on their calculator? It's just below the log button. No, you're not going to do second log. You're going to press the ln. Yeah, it can be negative.
Negative 2.25889.
Negative 2.25889. Beautiful. So, ln of e to the power 2x minus 1 equals ln 5. So this will go in front, and ln e is equal to 1. So that means this is just 2x minus 1 equals ln 5. Yes? So x equals ln 5 plus 1 divided by 2. So that is... Notice I skip a lot of steps. I hope you're good with that. 1.3047 blah, blah, blah. Yeah? Yeah? I saw some people doing this. It's a distributive property, ln x plus ln 1. That is no such thing. Cannot do that. Logs are very finicky. You cannot do that. You cannot do that. I see that all the time. You start making stuff up. You think you can do that. Okay, so what's the process for solving for a log? You need to get all the logs to one side. So ln of x plus 1 minus ln x equals 1. Then you got to write it as a single log. So ln of x plus 1 divided by x equals 1. Then you change it into exponential. What's the base of this ln? E. E to the power 1 equals x plus 1 divided by x. Cross multiply the x over. You get ex equals x plus 1. How do you solve for x? You need to get the x's to one side. So ex minus x equals 1. Factor out the x. X bracket e minus 1 equals 1. So what does x equal? 1 divided by e minus 1. And that's your answer, because this would be on the non-calculator part.